Hello, welcome to Picture Me Coding with Eric Aker and Mike Mall.
Hi, Mike.
Hey there, how's it going?
Pretty good. I have a cold this week, so you're the host and I'm the co-host.
Your co-host 9000 this week.
Yeah, your host 9000.
Sounds good. Let's talk about music.
Okay.
What's up with you this week?
Did you told me about John Martin, I think. Martyn, English
Yeah,
folk
so I
musician.
saw a review recently of an album of his called Solid Air, which I'd never heard of, but people talk about like being one of the great albums of all time. And
From 1973. Greatest album. I had never even heard of it.
yeah, not either, but it's on like a lot of top 500 albums of all time list sort of things.
I had this experience when I was 18 or 19 where people were like, Pet Sounds is the best album that's ever been recorded ever in all recorded music. And I was like, really? Let me be the judge of that. I listened to it. I was like, I've heard half of these songs. And yeah, actually, this is pretty good, isn't it? It's not a matter. I don't know about the greatest thing ever. So you told me about John Martin. I started listening to his first record, which is called London Conversation, and I kind of fell in love with it right away. It reminded me of Nick Drake. It's his English folk music from the '60s, '70s. He actually kept recording into the '80s and later. And Pink Moon from Nick Drake is for me one of the greatest things I've ever heard. It just transports me to this place that's so different from any other place I've gone to. This record kind of gives me vibes of that, and that's not bad. Like being connected to, he was friends with Nick Drake. Nick Drake sadly died really early.
Yeah,
But
I
then the one you
remember.
mentioned, Solid Air, is different and kind of an extension. It's not just this late '60s English folk. And in the '80s, he did a record with Phil Collins.
I think everybody did a record with Phil Collins in the 80s.
Oh, I didn't.
For those of you who weren't around in the 80s, Phil Collins was like literally every second song on the radio.
I just remember going into Fry's and they had their audio equipment set up, and it was like a glass room in with a bunch of just concrete and rows around it, and all these speakers all over the place, and they always had Phil Collins in the air tonight with that crazy drum solo like playing in that room, so you could hear how epic the audio was. And it would just be
Yeah,
the drums just going crazy in the and I associate Phil Collins with Fry's Electronics.
I miss the Fries. The one here in San Diego, they not only closed it down, they actually tore the building down.
Yeah, salted the earth even. How about you? What have you been listening to?
I've been listening to the new Bad Bunny album quite a bit.
Oh, I heard that one.
I've always been kind of a fan, but this one's especially good. I think sort of different styles, so like all Latin music styles, but not entirely reggaeton or hip hop. So it's very interesting. Almost every song is a good listen. I still don't really understand the Spanish very well, but I really like this album, and apparently everybody else does too. It's called Debí tirar más fotos, which basically translates to I should have taken more pictures.
It's I've seen a lot of people talking about it. You know that Bad Bunny has 86 million monthly listeners on Spotify.
I did not know that, but it does not surprise me. I would guess he's probably top 10, top 20.
Yeah, top one. So if somebody listening to us has not heard that album, maybe we can increment that by one.
Yeah, after this, I'll probably have 87 million listeners. So
87. Friends, if you want to reach us, please email us, podcast@picturemecoding.com. Let us know what you're thinking of the show. You can also rate and review the show on your podcast resources, such as Spotify and other places. We have a website, PictureMeCode, www.picturemecoding.com. We have a Blue Sky account, and we also have Patreon. If you would like to support some of the expenses associated with running our show, you can sign up to support us at Patreon. We have a $4 a month sponsorship level, and we will read your name aloud on the show to say thanks for your support. And all of the donations we get by Patreon are purely for running the show. So, editing, hosting, all those types of things.
So this week's topic is something that we sort of disagree on a little bit. I think not vehemently, but in a mild way. So the sort of title of our episode this week is "Do Programmers Need to Know Anything About Computers?" Obviously, that's a little bit tongue in cheek, I assume most programmers are probably more familiar with computers than the average non-programmer in
Mm-hmm.
any case. But basically, what I mean by that is, do software developers need to know anything about the underlying hardware of the computers that they're working on?
You start off by saying we disagree. So if this is debate club, what you're saying is Eric says we do not need to know anything about computers.
Yes, yes. My interpretation of your opinion is that anything more than lambda calculus is total corruption, and no. So I think you and I differ on this only to a certain extent. I think it's useful to know about assembly language and the details of memory and virtual memory and clock speeds and cores and
Mm-hmm.
that kind of thing. And
Mm-hmm.
my interpretation of your opinion is that you only sort of need to know about those things on a relatively abstract level.
Yeah, I don't know if I have such a solid idea, like a conscious opinion about this. I think I'm more, instead of us being in disagreement, it's more like you're a parent saying you should eat these vegetables, and I'm a child saying, when am I ever going to use these vegetables, Mike? If I have a job someday, I'm not going to need these vegetables to do my job, right?
But broccoli is good for you, Eric. Yeah.
Yeah, that's how it feels. So, how can we structure this conversation? One thing you could do is you could talk about types of knowledge that would be useful. Another thing you could do is you could quiz me on aspects of computer hardware that you think I should know as it relates to software. And that would be probably pretty embarrassing for me. People listening to us would be like, wait a minute, this guy has a job as a software engineer and he knows this little about hardware.
So I think a couple of things inspired this for me. One is that as I continually remind our listeners, I am very old. When I started programming, it was the days of the dinosaurs, and there was a little bit less of a separation between the software layer and the hardware layer. So if you were programming personal computers back in the late 70s, early 80s, through probably, you know, 85 or 86, you probably knew the hardware pretty well. A lot of people wrote assembly language back in those days. It wasn't uncommon to, drop down into assembly language to write something to make it a little more optimal. And, sometimes you were trying to squeeze out a little bit more memory. So you would, try to use fewer instructions and things like that. There was also probably people were a little bit more knowledge about the details of the operating systems, as primitive as they were. I knew things about the BIOS on my particular computer, and I knew things about the details of the MS DOS that was kind of the operating system of PC computers back in those days. And, by extension, I sort of think that knowing those things has helped me over the years, even when they weren't directly pertinent to the software that I was writing.
So let's take BIOS as an example. You knew about the BIOS on the computer that describe for our listeners what BIOS is.
So, BIOS, it stands for Basic Input Output System, or some people say other things, but from the listing of the BIOS that I have from my computer back in the days, it was the Basic Input Output System. And this
Hmm.
is software, but it's software that's actually coded onto a chip on the computer. So it's
It's not editable. It's part of the hardware.
it's part of the hardware, firmware, I guess you might call it. When your computer is starting up, it's relying on elements of the BIOS to get going and connect you to, the keyboard, the monitor, and that kind of stuff.
Because the
Yeah,
operating system itself is like a program that needs to be run, but something needs to figure out how to be able to run a program such as that.
that's right. Yeah. So you need this sort of sequence at the beginning when your computer is turning on that loads up the operating system and sort of starts that off. There were also aspects of the BIOS that you could use to control devices.
Mm,
So, in my early days, the storage devices were either, 5.25-inch floppy disks, or if you were a rich person, you might have a hard drive, a spinning disk sort of hard drive.
hmm.
And both of those could be controlled through the BIOS through what they call the hardware interrupt.
But you didn't continue to know about the BIOS on every computer that you used after that, right? And there are some computers where they don't even want you getting in, mucking around in there. This is like a proprietary thing. So knowing that it's not something that it's not knowledge that you have today about the computer that you use. And so what you're saying is not, I should know the BIOS on the computers I'm interacting with. I should be able to hack those things and get in there and muck around with how the operating system starts. You're saying there's something abstract that's useful there. There's some knowledge that's important to you.
Yeah, even to this point in time, I think it's useful to know, what happens when a computer starts up. About a year ago, I realized that computers have reached a point at this point in history where they are pretty complicated,
Hmm.
vastly more complicated than they were 40 years ago when I started out. And so I went back and tried to figure out these things again. My day to day computer, MacBook Air with an M2 chip in it. So I started to think about, what is the equivalent of these things today? What
Hmm.
happens when my computer starts up? What happens when I make a system call? What happens when I run a program? My take is that those things are both interesting and also somewhat useful to even a programmer who's not a specialist at the hardware level.
Yeah, I guess I'd like to know what is useful. There's something nostalgic in what you're saying. I don't want to dismiss it in that way, but you know what it reminds me of? It reminds me of talking to people who work on cars. There's a certain trend in the world of people who work on automobiles where there's this moment where cars in the evolution, their history, they transitioned from a thing where people felt like I can hold all this in my head to objects where it was significantly difficult to hold a lot of the working components in your head. And a lot of this had to do with the introduction of computers and electronics and stuff. I remember in college, I bought this. I bought for $1,000 a vehicle called an Oldsmobile Omega from 1979. I took it to my friend Steve's house, and Steve used to always work on cars. And he opened up the hood of the car, and he goes, "Oh, this was a sad era for cars." And I just started laughing. I was like, "What do you mean?" He was like, "They were starting to add these electronics, but it's early days for those electronics. The AC on this '79 Oldsmobile Omega didn't work by the time I had it." He sort of starts reaching into the engine compartment and starts just tearing stuff out. Like, you don't need this. They bolted on this. You're not going to need AC. He tore the AC out entirely. And if you look at the like pre 70s era for cars, that's this era or early 70s, a lot of those car people sort of look fondly on the vehicles from that time. And if you open up the engine compartment on one of those things, there's so much room in there. You could like crawl in and hug the motor. And you can immediately build abstractions for the stuff in there with a handful of concepts in your head. And then as you go to the 80s and beyond, you open up the hood of a car and you could sort of still see the components. You could see the motor, you could see pistons and things, but you can't see the pistons obviously, but you could sort of see you could imagine the spark plugs go there, and it's a combustion engine, right? Not talking electric motors here, but there's so much electronics involved that if something goes wrong with the computer, you got to plug in the code reader, and there are people out there who are like, we've really lost something here. Is that the kind of argument you're making, Mike?
Um, it's not the kind of argument that I intend to make, but I think there may be a little bit of a sort of shade tree mechanic nostalgia in my viewpoint. You
It's kind
know,
of like, do you remember when you can hold all this stuff in your head? Is that what you're saying?
yeah. Well, I mean, that's part of it. I think they're like with the car analogy. They're I think what people are lamenting is that it used to be that if you were a mechanically inclined person, you could you know, change your spark plugs on a weekend or that kind of thing. And now, even relatively routine maintenance has gotten kind of onerous. There's cars
Hmm.
where if you want to replace the oil filter, you have to remove the engine and that kind of thing. So, yeah, I fear that there probably is a little bit of that, like wishing that I could still do the sort of weird and slightly mischievous things that I did
Hmm.
back in the '80s. When computers had a lot less protection on them.
Where you could like remap keys to send other codes.
Yeah. So, like the analogy with the cars is, It's hard now to do your own repairs, but there are people who do that. There's highly trained mechanics who still specialize in being able to do this maintenance, and so it's not like it can't be done anymore. It's just you need to be a specialist in that. And we have this sort of similar thing in computers where there are people who, for whom, this is really their job, is thinking about hardware and low level details of the operating system. You've got embedded programmers who may be working on they may be working on like operating systems that are not mainstream things, or where they need to put code into like a firmware or something. And then you've
Yeah,
got
so embedded programmers, they're not going to just argue with what you're saying, certainly. You're
yeah,
talking to a different audience, I think.
yeah, an embedded programmer is going to say, well, of course I need to know about the hardware, and even a system programmer, somebody who's doing Linux kernel programming or something like that is probably going to say, yeah, I need to be fairly familiar with the hardware because, I'm writing device drivers or I'm writing schedulers, or,
Mm-hmm.
there's specific things about CPUs that I need to account for.
But wait, you look at me, you know the work I do. I write Python or Rust, I put it on Kubernetes pods. Are you saying, Eric, you should be able to read or write everything that you do in assembly? You should be able to read hex dumps. Is that what you're telling me?
um, I don't think you should be able to write everything in assembly. Um, I do think you should probably be able to read hex dumps. I suppose there's a bit of a debate on that.
Why? Can you tell me why? What's the benefit to me to reading hex dumps? Hex dumps, we should define that. Can you define that one? This is your topic.
Well, two possibilities here. So, one is like you're running a program and it core dumps and leaves this binary image behind that is the state of the program when it went haywire, and
Like it's what was in
what
memory
was
when
in
it
memory.
failed.
And there are people who will have the knowledge to be able to analyze we call it a hex dump because people will often view this as a set of hexadecimal numbers. And there are people with specialized knowledge who can look at that hex dump and figure out, what state the program got in and why it had a bug, or why it core dumped. So I don't necessarily think that everybody should have the specialized knowledge to be able to analyze a core dump. But here's an example, I think, of what I've come across and what makes me think that people should have a little bit more knowledge about this. So I've talked to people who are working programmers who, are doing, say, relatively sophisticated web applications or something like that, and they're doing Python or maybe Ruby or Go or something like that, and they're deploying it to a cloud platform.
Hmm.
And they probably would not even understand what a core dump is. I,
You
I've
don't think so?
I've
Like if you
talked
said, "Hey, go ahead,
yeah,
go
I've
ahead."
talked to people who don't even really understand the idea that the program code and the data is in the same memory.
Okay.
And I think,
I'm trying to in my head. I'm trying to weigh the people I've worked with.
uh,
What even understanding? Go ahead. All right, go ahead, go ahead.
so
It's like I want to know what's the value of thinking in that way for the people who are working on these things.
so like this has been the architecture of computers since the 1940s, and
The von Neumann machine, right? You load the. Isn't
yeah,
that it?
this
Right?
sort
That
of
was the
idea
von
that
Neumann machine.
the code and the data are in the same memory has gone back to at least the EDVAC and von Neumann, which was
And probably the immediate response is, well, wait a minute. Can my code can I build data structures in memory that overwrite the actual program that I've written, and then it starts doing weird stuff? Can that happen?
yeah. So maybe this doesn't matter to you unless you're doing something like C programming where you could actually have a buffer overflow or something like that.
You can make a beautiful mistake, but like that. Is that what we call undefined behavior?
But anyway, I think that's a useful thing to know, even if you never have to look at the core dump yourself or you don't understand what's in there. I think it's useful to know that that is a thing, and that in that core dump, you're looking at sort of a memory image of your program. I've been surprised by the number of people who really don't understand that that's happening or that that's going on.
I guess I do have doubts that this is going to be really broadly applicable. I guess there's a lot I could say in response. Here's number one, what I would say. If you gave me a list in your lengthy tenure as a software developer, you said to me, Eric, these are like the hardware level things you should try to understand. And this is the level of detail your knowledge should extend to. I'd be so happy to receive that list. But
Uh,
before that, I do wonder if what you're talking about really does have to do with specialization. You already talked about embedded developers, but there's two kinds of specialization we might be talking about here. One is specialization in skill and experience. That happens in any field when there's enough work to sort of go deep into different areas. So if I specialize, or even if I kind of have broad knowledge of a certain set of areas, I guess, of knowledge, do I also need this? And there's a different kind of specialization. When you talk about bias, made me think, well, isn't that really hyper specific? And what is specialized also is not just the experience, the roles that we take on, but the run times that we're deploying stuff to is pretty specialized these days. I mean, you gave the example of deploying stuff to cloud. It's like if I put something in a Docker image, I run it on Kubernetes, there's quite a lot of layers to actually get down to a real hardware. And someone who is deploying stuff in a public cloud doesn't have a lot of tools to reach all the way down to that hardware layer, right? I'm like obstructed from it by design.
I think that's true, but I think the core of the argument that I'm getting into is that having some experience with these things, even if you don't encounter them on your regular day to day work, gives you a sort of intuition about what's
Mm.
going on, even when you're several levels removed from the actual hardware.
Okay, I like this argument. And you know what? I believe you. Are you ready to give me a list of the things I should have intuition about? Or is that too hard, too specific for what we're talking about right now?
Well, I think there are some things, and people will probably debate the connection here. But so one thing that I thought of that we have encountered together in the past is when you're deploying things to a platform like Kubernetes. Sometimes, well, you generally will end up specifying limits on CPU and memory.
Okay, so CPU limits and memory. We had a whole episode about that, and I did lean pretty heavily on your knowledge about how CPUs work and how the completely fair scheduler works. This is one area where if you're going to deal with assigning resources to Kubernetes pods, it helps to understand what it means to request CPU or limit CPU. And that's an abstraction that goes pretty deep, yeah.
Yeah, CPU, like even now, if you go out and look at advice on how to set CPU limits on Kubernetes, you'll get differing arguments.
This came up just like it comes up like every week on social media. And I don't think that's an exaggeration.
Yeah. And, I think part of the reason why it's difficult is because you have to have a considerable amount of knowledge on both the hardware and operating system level to understand why it matters. To get this right, or to at least understand how to optimize this, I think you do need to know something about the underlying machines that your Kubernetes cluster is running on. How many cores do those machines have? And then I think you need to know something about the way things get scheduled, which is also a little bit dependent on both hardware and operating system knowledge. And I think, sort of a related thing here is that I think that what happens in a lot of these cases is because people don't have a strong intuition about how processes interact and how CPU cores are utilized and how memory is utilized. I think people just basically over provision their clusters
Hmm.
considerably so that they just make the problems go away as much as possible.
I would agree with you on over provisioning just based on my experience. I don't know if it comes from not having intuition about how stuff works at the lower level. If you were to say to me, hey, people over provision cloud resources, why do they do that? My guess, this is just a guess, would be that it's hard to predict the needs of workloads before you run them and you just collect data on what they're doing.
Yeah, I think that's probably true as well. But I do think that what happens is that you get into this sort of arms race where, you have people deploying different workloads and they're not really cooperating with each other, and so they they see that their workload gets out of memory killed or something like that, and so they just increase the memory limits. And
Yeah, I've been on the other side of that conversation. I've tried to talk a lot of people off that cliff over the last 5 years. Like, oh, hold on. Can we see why it's needing that much?
yeah,
I have been in the room having that
yeah.
conversation.
So I think people do. They just sort of increase limits until eventually something becomes unschedulable.
And then
So
you increase the node count.
yeah,
We're
yeah.
talking a lot about Kubernetes here, but is there a limit? So you're saying broadly, I should know about kernel scheduling, I should know about hardware, I should know about CPUs in order to understand when I'm assigning resources to a Kubernetes pod. Okay, cool. What knowledge, how far do I need to go? What would be the learning plan to build that intuition?
Yeah, it's a good question. I have asked myself, how far down the rabbit hole do you go before you realize that you're no longer the returns are diminishing. I think that in most cases, you probably don't need to know the specifics of, like, you don't, maybe you're running on Intel AMD microprocessors, or maybe you're running on ARM processors or something like that. And maybe you don't need to know the difference between how the cores in those two CPUs differ. Maybe you don't need to
Mhm.
know the clock speeds, but I think it does help to know, how many nodes are in my cluster, how many cores do those nodes have.
What does it mean to assign CPU? And we tried to cover this in our other episode, I think.
Yeah, the basis of my argument, I guess, is that if you have worked in the past at a lower level and you understand the hardware to some extent, it gives you an intuition about how to approach setting these limits and using the cluster more efficiently.
So, one example you're giving here, CPU scheduling, resource limits. Do you have other examples of knowledge that would be a benefit to me as a software developer, as an application developer, or data engineer, or some of the other?
So, like, another thing that came up for me, a lot of concurrency models are based on they're based on abstractions, but fundamentally those abstractions relate to the underlying hardware. So, the three things that people are probably going to encounter at some level in any programming job are the type of concurrency that you see in things like Python Starlet, the ASGI interface, or Node.js, that type
Event
of,
loop, async stuff.
yeah, the sort of event loop async type of concurrency. Or you will encounter a multi-threaded situation, or
Let
possibly,
go.
yeah, like Go, or like, if you're using certain web servers, like Apache was a multi-threaded situation, at least back when I was using it. And also, you may end up doing multi-process things. And my experience has been that a lot of times when people are encountering these things for the first time, they really don't understand the differences, and they really don't understand what's happening when they're
So
when
you're
they
saying the difference in this case between like an async event loop versus multi-threading, and we can break that up into different categories, right? System threads and green threads, probably,
yeah.
and multi-processing. You're saying that this is knowledge that when you in your peers, when you worked with people on teams, maybe I'm not using the word peers right, but like in your coworkers, that they don't seem to immediately grasp or have intuition for.
Yeah, and they don't understand, I think, the trade-offs between one approach and the other. There are cases where some of these models are the right thing, and other models would probably be less appealing or less
I
performant.
am I wrong in thinking this is kind of? I don't want to be like a gatekeeper here, or like I sort of am concerned about specialization. But to me, the knowledge you're talking about when you talk about threading, system threads, green threads, multiprocessing, async, that's sort of like intermediate level software developer knowledge, right? Like once you've been working for 5+ years, you probably have some grasp of this. That's what I would guess. This is a guess. I don't know. Maybe not if you're working specifically on front end development. And that's not a judgment, but maybe you don't have to know those things.
So this is maybe a little bit of curmudgeon coming out, but I think you would be surprised if you were to talk to people about this, how much they are just sort of using, so how much they're sort of relying on a pattern that was established for them. If you talk to, like, I've worked with, hope nobody will take this personally if I've worked with them in the past, because I'm not identifying anyone in particular here. But so in the course of our career, for instance, like we started out with Django and then went to Flask and then went to Starlet. There's a difference between the way Flask and Starlet operate in terms of
Mm-hmm.
their concurrency model, or
Mm-hmm.
what.
Starlet's async, Flask is sync. But actually,
Yeah,
you could do async and Flask finally, but
yeah,
for most of its history.
yeah. And so there's like cases where you might have been doing a Flask thing, and then you ran into some long running process, and so you introduced something like Celery or some other distributed task queue because you had
Mm-hmm.
this long running background process. And if you're working with Starlet or Fast API or something like that, you might not do that. You might have some option where you can start off a concurrent routine that is just being executed by the event loop. So you
Mm.
don't you don't need a separate process to run that thing. And I I think you would be surprised at how many people have just sort of taken the patterns that have been given to them, and they don't really understand that there's actually something different happening there, and that
Hmm.
the differences between what's happening there in the two cases is significant.
Yeah, I guess if you're using the Python async frameworks are based on this ASGI, which is a interface that was created by the Python community to say when we build async frameworks, they will have this protocol. They'll take inputs like this, they'll have outputs like this, you'll have functions that run at these moments in time. So you write a thing that conforms to that protocol, and congratulations, you've written an async Python framework. The interesting thing about this protocol is it allows for background. So with async, you can schedule all kinds of async tasks, and you've got an event loop which runs around and it loops and it checks if tasks are ready to continue processing. Right, so you can kind of hand off async tasks at await points. You park them somewhere in the kernel. Here's my lack of knowledge of whatever epoll or what is it, kpoll. What's the Linux thing that does the async?
Uh, I don't know. I'd have to look it up.
Yeah, it's something one of those, right? You park them in the background and they continue to make some progress. Often they're doing like, hey, let me call out to this other resource and just wait for a response to come back. And then when the response comes back, at some point the kernel says, hey, this thing is ready to wake back up, and it puts that task back to me so that in my program anyway, so that I can continue processing. And in the async gateway interface, the protocol that they wrote in Python, they said, well, we could also do background. So you could receive a request, send a response in the background, kick off a task, and that sounds really cool. But you're right, it is significantly different from like a Celery, which is a whole other dedicated process with its own process manager that's going to keep it running, that's going to keep track of whether or not the thing that you've scheduled has actually completed or not. If I run something in the background and then meanwhile some other request comes into my server that's so large it takes the whole server down, well, my background task goes down too. I actually had a conversation about this recently because someone had released a library. It was one of their first, they said, this is one of my first open source libraries. And they said they had built all of this machinery around calling background tasks. And my response was, oh, that's kind of cool. But if I'm going to go to the effort, I'm probably not going to use background tasks because I care about them getting completed. So I'm going to hand them off to something like a Celery or something else. And they kind of didn't quite get this critique. I wasn't trying to say, no, 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 don't do that. I was trying to say, I don't think I would do that. And I think underlying was exactly what you're saying. The person who had worked on that didn't think in terms of, I've got a web server and it's also doing background tasks. What happens if the web server stops? Obviously, every background task in memory just gets ditched. Does that matter to me? And I was trying to say it matters. And there's like a sort of kernel operating system, what's in memory. There's some of that intuition is required for that question. So you've given a couple of examples of knowledge that you think would be beneficial, and I want to get to more of them. You gave the example of CPU limits in Kubernetes, CPU requests in Kubernetes, and understanding what it means to schedule a program and what it means to use CPU or reserve CPU. You also gave the example of concurrency and parallelism, and I can kind of see that. We haven't quite got down to hardware level parallelism, but you know what? So the word that you used that was like a magnetic attraction in my brain for these things. You use this word, which I really like, but I think has a lot of weight and assumptions and ideas sort of magically bound up in it. You use the word intuition. I like this word because I think this is where your argument is most cogent. If you say to me, hey, you will hit problems in your career where if you have intuition for X, it can really help you think through the boundaries of the problem, what's going on in that problem. You're building intuition, it helps you be ready, be prepared for what you encounter in the future. But I can't just hear this term intuition and I think, well, what does that actually mean? What am I doing when I build intuition? And it recalls to me something that I heard recently on a podcast called The Gray Area. Someone sent me this episode of this podcast. I'd never heard the podcast before. The episode's called Your Mind Needs Chaos. And there was a academic interviewed on the podcast. His name's Mark Miller. He works in neuroscience, cognitive science, and like philosophy of the brain, interestingly. He described this thing which in cognitive science now they call the automatic inference framework. I'll just try to give a very, very quick description of it. The automatic inference framework is this contemporary theory that the way the human brain works is it builds models about the world and it then builds predictions about its environment. And sensory data is purely to tune those predictions. So we really only have enough sensory data coming in to build and tune predictions about our environment. And they have all kinds of examples about how this might relate to typical human behavior, but also like pathological human behavior. Like, oh, I'm interacting with social media and I have poor expectations. Like, it's making me feel bad. Why is that? And there's a whole paper they wrote that I was reading about how the automatic inference framework says, your model's not working. And when you feel your model not working, it's like it's painful and you try to correct it. So when you say intuition, I've been thinking about this for weeks since I've heard this episode. It makes me think, well, maybe intuition is about building the mental model to be able to predict the behavior of a thing in its environment. How does that sound pretty far off out in space, or is that close to what you're describing when you're talking about intuition for things?
I think there might be a connection in that, if your brain is trying to predict things, it probably helps to know that there's probably some extent to which your brain incorporates what it knows about the physical world. Maybe younger people, I don't know how this actually works, but maybe when you're younger, it doesn't make sense to you that if you throw a rock, it's gonna eventually hit the ground again. Maybe that's something you don't know when you're a toddler. I don't know.
Wow, that goes right back to David Hume, Mike. Hume with the billiard balls guy, right? Cause and effect. The first time you see the cause and effect, you could not have predicted it, but then it just becomes a thing you know about your world.
I listened to that episode too, and I don't remember it entirely, but I can't remember what they said about how your brain incorporates knowledge into its prediction machine. But I guess my argument would be that if you look at a problem and you can't figure it out, and there's sort of an infinity of paths that you can take, having a certain amount of knowledge about things maybe culls down the options that you explore. I don't know. Maybe that's also true with the prediction model in your brain that's trying to figure out whether or not that rock's going to hit you in the face.
Pruning options of exploration space. That's pretty good. It still sounds to me like you're talking about you were able to acquire abstractions from your interaction with computer hardware, but you're not saying you have to understand the hardware. It sounds like what you're saying is these abstractions are really useful, which makes you wonder, are there other ways to acquire those abstractions, to gain intuition for them? And we still kind of don't have quite a list for them. So far we have kind of CPU and scheduling, we have concurrency. These are great things to think about abstractly at the lower level. What other things would you put in there?
Well, I think everything else tends to get a little bit more in the weeds, as people say.
Mm.
Possibly another example is, many years ago, this is probably going back 15 years or so now, the company that I was working for wanted to build its own auto scaler.
What's autoscaler mean in that case?
Well, so we were in the early days of deploying stuff to the cloud, and it was before Kubernetes and ECS and stuff like that. And so we were trying to figure out, is there a way that we can, spin up new servers when
Oh,
we get
okay.
hit with more traffic,
Got it. Got it. Got it.
and we didn't really have capacity to, put our own engineers on it. So we decided, we were close to University of California, San Diego, so we were going to hire an intern to work on this over a summer and see if they could make any progress on it. And so we interviewed a bunch of grad students and a couple of undergrads, and basically we were trying to ask them what they knew about, why would a web service start to get slow?
Hmm.
Why would the latency increase on a web service? And
Now, these are people without actual industry experience.
yeah,
They're undergrads. Grad students might have industry experience.
yeah, not much industry experience, but people who are going through a pretty prestigious computer science curriculum.
And early days of the web, I think, is a footnote here. This is
Yeah,
15 years ago, you said.
yeah, this would have been, Apache was probably the top game in town. Might have even been before Nginx. I'm not sure. So I was kind of surprised at the time that most of the answers that I got about why a web service would get slower had to do with algorithmic concerns. So,
Oh,
people would say, well, you probably need to optimize the code to make the calculations run faster, and got very few answers about, resource contention or, memory usage or whatever. And so I was, I, this is a thing where I think people, you have to have worked for a certain amount of time to understand that these things happen. And you also have to have a little bit of knowledge about how computers work to understand why they happen.
it's funny because you mentioned this comment, and I immediately think resource contention.
Yeah.
People come to me with questions at my job all the time, and my first response is, I guess we'll check if there's resource contention. but I would not claim to be someone with hardware knowledge, the kind of knowledge you're describing as useful.
Yeah. I mean, this is probably a case where you probably don't need to know if the core on your CPUs are hyperthreading or whatever. I just think it's interesting that I think this has to do a little bit with this kind of distributed stuff that we've talked about in various episodes over the last year as well, and that I think people don't really understand the consequences of what happens when you start having multiple processes trying to talk to things over a network or an interprocess communication channel.
Here's a question for you. We've talked about like field specialization. We've talked about runtime specialization a little bit, like maybe I'm deploying into cloud, maybe I'm deploying onto raw metal, as they say. What about like in a lot of cases, you'll hear developers say, "Oh, I don't have to worry too much about making it go faster. It's usually fast enough." Maybe there's a specialization in optimization too. Like maybe that's a specialized type of thing. Sometimes I'll see descriptions of data structures, and in the description of the data structure, they're saying we're trying to make it go faster and faster. They'll start talking about cache buffering, like pages that are getting cached, and saying we want the structure represented in our code, make it easier to have everything we need in a single page of caching. That, and when I read that, I think, well, that sounds pretty hyper specialized. Would you argue, no, that's not that specialized? People should be aware of that type of optimization, that it is possible and even necessary sometimes.
I would probably argue that, yes.
Was
And
my terminology even right? I wasn't even sure if I was using the right terms there.
well, so we've talked about this a little bit. So I think my argument about hardware may just be an argument about abstraction and more broadly. So, like two cases that come up a lot in this business are, you see this argument from time to time about, do computer programmers need to know anything about math? And there's always a bit of a debate about it, because clearly a lot of programmers are doing interesting stuff without having deep grounding in mathematics. And in computer science, of course, when you're talking about mathematics, you're probably not talking about like calculus and differential equations. You're probably talking about discrete math. Does it help to know graph theory, or does it help to know computational complexity, or does it help to
Yeah,
know?
there's tons of specializations within mathematics too. I mean, when you
Yeah,
say knowing math, it's like, well, which math?
right. And even like data structure stuff. Back when I started out, if you needed a linked list, you probably had to write a linked list. If you needed to sort something, you might have to write a sort algorithm. And it was probably much more important to know the subtleties of, quick sort versus some more brute force method. And, now you just probably have a language that does a sort for you and it's already optimized. So you might not ever have to think about that on a day to day basis. But I guess my argument with those things, as with my argument with the hardware, is all things being equal, the person who has some grounding in discrete math or the person who has some grounding in data structures is going to be better off than the person who doesn't. Again, all things being equal.
I have kind of an observation that I think is going to make you cringe. Often, you don't actually have to understand problems to make them go away. I will admit at many times in my career to not going deep enough and fully understanding what a problem was and still solving it. Solving it in terms of making it go away. And maybe the fear is, well, are you sure? I can give you an example from just this week if you want. But I'm admitting that I have solved problems I did not understand before. And I want to say I've met a lot of people in my career who've done this. They'll come to me with a pull request and they're solving a problem. And I'll say, oh, but what about, did you think about this? And they're like, oh, this just goes around the problem. The problem just goes away when you do this thing. And there's this feeling I have a response of, oh, but we don't actually understand the problem. Is that going to hinder us? I'll give you an example, but does this sound familiar to you? Have you ever solved a problem you didn't understand, Mike?
Sure. I mean, I think everybody encounters this situation where, you might have a Heisenberg and it goes away by rearranging some code, or sometimes you work really hard on solving a problem and then realize you don't actually need that thing that you're building anyway. But I guess the situation I'm sort of imagining is, I believe in I believe in the philosophy of not prematurely optimizing things. So
Hmm.
make it work first and then make it fast. But when you reach that point where making it fast no longer is optional, there's going to be certain knowledge that is going to help you fix that problem, I believe. Like understanding some aspects of computational complexity, knowing a better algorithm, knowing a better data structure, knowledge of those things probably helps you over somebody who does not have that knowledge.
I guess I could give you this example that I had this week. I'm not sure if this example is really going to work out here. I'll give it a shot. I have a Kubernetes pod and it's sending requests to a gRPC server. gRPC, specific protocol over HTTP2, and the Kubernetes pod is participating in what's called a service mesh. And so all of its requests go out over the mesh. And the mesh provides some benefits and it provides some analysis and it provides some different strategies for routing and retries and all. It's got some interesting stuff. So that's the basic setup. I've got a client, it's sending a gRPC request, it goes over a service mesh. And I'm seeing these error messages. Now, the actual request is working fine, but the service mesh is telling me, hey, this connection was kept alive too long, so we closed it for you. And I'm like, what? I'm not trying to keep that connection alive. And so I start kind of drilling in. The client that I'm using is calling into library code, which is calling other library code, and it does not look like it's trying to keep the connection alive. There's all these layers of software. There's a heap of software between me and the computer. Ultimately, what's happening is my program is opening a socket, it's sending data down the pipe that's going to a server, it's getting a response. And the question that I have right now is who's keeping that connection open? Am I? I don't think I am. And I figured out very quickly how to quote unquote solve the problem by making it go away. If I just don't use the service mesh, then the problem goes away. There's nobody complaining about open sockets. But now I have this deeper question, which is, am I keeping those sockets open? And to answer that question, I'm going to have to probably go pretty deep. I just started exploring this yesterday at work. I might have to do like a net top type of thing where I'm looking at, are my connections still alive? I might have to look at system calls to figure out if that connection gets closed. There's a lot of other things I may have to do to go deeper and deeper and deeper to figure this out. But at this point, I'm like, well, maybe I'll just skip it, and then I'll go and look at my observability tools and see if if these connections are closed at the same rate that they're opened from outside. That might be good enough. And this is an example of, do I really need to know the problem? And to me, this is the dirty secret of what we do. It's really common that people don't fully understand a problem that they solve.
Yeah, that I think is true, and I don't think it's necessarily always bad. You and I have discussed that while I think it's useful to know these things, it's probably also difficult to keep all of it in your brain. And there's
Yeah.
probably some extent to which trying to keep the most important things in your brain is more important than trying to keep everything in your brain.
Yeah. There's a limit, right? There's a limit on time. How much time do I have to learn all these things? Is there a limit to memory? Probably.
But even what you're describing, the problem you're describing, even if you don't fix it at the most, basic core root problem level, you are demonstrating a certain amount of knowledge about what's going on there. There are people who are, I believe, there are probably people who are doing this work who probably wouldn't even really understand that there's a socket getting opened at some point in this process.
You gave me a little gold star there. I don't feel like I deserve it though. I feel like there's
uh,
so much stuff I don't know. Mike, I want to read to you from one of my favorite novels ever. The book is called White Noise. I when we first became friends, I told you got to read this book. I forced you to read it. There's a famous chapter in White Noise called The Airborne Toxic Event, where there's this toxic cloud over their town and they have to flee for their lives. And the end of that, it's a very long chapter in the very middle of the book. At the end of that chapter, they're huddled in like a refugee center, um, evacuation center, I guess would be the word for it, not refugee center. They're huddled in this evacuation center, and the narrator of the book is talking to his son. And his son is like kind of nerdy kid. He's been collecting information about this event that's happened, try to figure it out. And the dad, the narrator character, is unsettled, like, wow, there was this incredible industrial accident, and are we gonna die? He says to his son, well, it's comforting that there are people out there who know what's going on, right? They're taking care of us. They're sort of like they have the knowledge to answer. And the son responds, I've never forgotten this. I read this book over 25 years ago. It's one of my favorite books. This is what the son says. He says, it's like we've been flung back in time. Here we are in the Stone Age, knowing all these great things after centuries of progress, but what can we do to make life easier for Stone Agers? Can we make a refrigerator? Can we even explain how it works? What is electricity? What is light? We experience these things every day of our lives, but what good does it do if we find ourselves hurled back in time and we can't even tell people the basic principles, much less actually make something that would improve conditions? Name one thing you could make, he says to his dad.
yeah, I'm sometimes overwhelmed by thinking about my specific computer and how it would be incredibly hard to recreate. Just thinking about there's multiple countries and logistics and where do you stop? I used to make this joke about how when my kids were young and they started asking the standard questions about why is the sky blue and why is grass green and stuff like that. It's that eventually you end up having to explain quantum mechanics to them.
Yeah. How beneficial is it for that 8-year-old to know, well, there's a lot of nitrogen in the atmosphere, right? Does that help them?
Yeah, well, let me first explain about the electromagnetic spectrum, and then we can get on to why grass is green. I also remember reading this thing years ago. This has probably been 25 years ago now, but somebody did this kind of. It was supposed to be funny, but they were talking to Harvard graduates, like literally at their graduation ceremony, and these are what you would expect to be the best and brightest. And the question that they were asking them is, why does it get cold in the winter? And something like 75% of these Harvard graduates either did not know or gave the wrong answer to why does it get cold in the winter.
What?
I confess, even though I think it's useful and helpful to know this stuff and it will help you develop intuition about programming in the large, I also confess that there's always going to be more that you don't know than you do know. So it's kind of a,
It's daunting.
yeah, even with computers, I to satisfy my own curiosity, I've been kind of writing down stuff about how my Mac works, and it's really kind of depressing to realize how little I know about it and how deeply I would have to go to understand everything about it. I downloaded the architecture manual for the ARM processors, and I thought, this is probably going to be too technical for me, but I'll take a look at it. And I was kind of curious about things like how are the machine code instructions formatted and stuff like that. Anyway, the punchline is the ARM architecture reference manual PDF is 15,000 pages long.
Wow.
So there's not much chance that anybody out there knows everything about the ARM processor in the Macintosh. Probably not even the people who, designed the Macintosh. They probably don't know everything there is to know about the ARM processor. So,
This conversation at White Noise continues. The son says, if you came awake tomorrow in the Middle Ages and there was an epidemic raging, what could you do to stop it, knowing what you know about the progress of medicines and diseases? Here it is practically the 21st century. You've read hundreds of books and magazines and seen 100 TV shows about science and medicine. Could you tell those people one little crucial thing that might save 500,000 lives? Boil your water, the dad says. I'd tell them. And he says, sure, what about wash behind your ears? That's about as good. You come alive in the time of the Stone Age, could you build a refrigerator? You come alive in the time of the Middle Ages, could you tell people things that would solve major pains? And a lot of the knowledge that we have, that like the knowledge that just is outside of my knowledge, often just seems like magic. And this is a theme in this book, actually. So if you show up in the Middle Ages and you're trying to describe penicillin or radios, everything you would describe would sound very magical. And the only way you could be, well, there's like tiny little creatures that you can't see, and
right.
make you
Yeah.
sick. And there's frequencies of light that you cannot see. And it's like, okay, you're talking about angels and magic and things like that.
Yes. And we're probably going to have to burn you at stake now. When I was in college, I was a chemistry major, and my roommate was also a chemistry major. And he came home one day, and he was taking a thermodynamics class, and he said, "We learned about this really cool thing today called the Joule Thomson effect. It's really amazing. We need to figure out some way to invent something around this." The next day, he came back and he said to me, "Okay, never mind. It turns out people are already using this in inventions. It's called the refrigerator." So
Did we end up with a list? People listen to us for listicles. Did we end up with a list of knowledge? It sounded like CPU scheduling, in your opinion, useful. Concurrency topics, concurrency and parallelism topics, useful. Was caching in there, or it's diminishing returns? Like, yeah, sort of useful sometimes.
yeah, I think caching is useful. Caching, I think, is an interesting idea in particular because of the fact that it is used at so many levels. Like the CPU in my Mac has 2 levels of CPU cache, and that's before you even get into actual application programs where you might have
Hmm.
your own caches. But I don't know exactly what the boil your water equivalent is here. Like, what's the one thing you need to know?
Let me give you one
So
last section from this white noise chapter. The dad says, I think we're doing pretty well. Again, they're in an evacuation center. There's been this massive industrial accident. We have food, we have radios. His son says, what's a radio? What's the principle of a radio? Go ahead, explain. You're sitting in the middle of this circle of people. They use pebble tools. They eat grubs. Explain a radio. And the dad says, there's no mystery. Powerful transmitters send signals. They travel through the air to be picked up by receivers. And the son says, they travel through the air. What, like birds? Why not tell them magic? They travel through the air in magic waves. What is a nucleotide? You don't know, do you? Sidebar, Eric, I have no idea what a nucleotide is. He says, yet these are the building blocks of life. What good is knowledge if it just floats in the air? It goes from computer to computer. It changes and grows every second of every day. But nobody actually knows anything.
I do know what a nucleotide is, but I still don't think I could explain it to people in, prior to the knowledge about atoms.
So Heinrich concludes nobody knows anything. And I think what he's saying is there's always some kind of cognitive offloading where you may have learned this thing in school or in college or whatever, but you couldn't explain it from scratch to somebody. Maybe there are things that you where you have that knowledge. But for most of the contemporary knowledge, it's so expansive. You can't hold it all in your head. You kind of specialize on things. And Heinrich concludes, well, nobody knows anything then, which goes pretty far.
It does feel like that sometimes, especially these days. You probably know this, but there's this famous the thing that Richard Feynman proposed at one point in time. So he had this sort of thought experiment about civilization is going to end, all the people are going to disappear, but the planet will still be habitable, and there will be human beings around who can repopulate the earth and restart civilization, but they have no prior knowledge. They have no knowledge of the prior world, and so his thought experiment was, what piece of information would you pass on to them that they could conceivably understand that would help them the most in terms of rebuilding civilization? Feynman's answer to that question was the idea that matter is made up of atoms. I think that's probably would be hard for people to understand, but I think that is probably a pretty good place to start.
I'd probably tell them, whatever you do, don't invent plastic. Find some other thing that solves the same need.
Buy Google stock.
All right, Mike. I started out thinking, well, Mike's going to make me feel bad here for all the stuff I didn't know. You never really quizzed me. You even gave me a gold star that I didn't deserve partway through.
Yeah, I was going to ask you about single instruction, multiple data, but just because I like to say SIMD.
I'm going to take an F on that one.
Fair enough.
All right, this has been Picture Me Coding with Eric Aker and Mike Mull. If you want to reach us, podcast at Picture Me Coding. If you want to support the show, we are on Patreon at Picture Me Coding, patreon.com, Picture Me Coding. And we will see you again next week. Thanks, Mike.
See you next time.
Bye-bye.